States of matter. There are famously three: liquid, solid, and gas. But what if I said there was a fourth? Not plasma, but liquid crystals. But what are liquid crystals and how do they work? Well, let's take a look. In order for something to be classified as a liquid crystal, it has to be stable. It also has to have an anisotropy of properties, and this is very complex, but what it means is variations along the molecular axis, and what this means is variations along the axis with the most symmetry. For example, with this molecule of ethane here, there are 4 possible lines of symmetry, 1 across, 1 down, and 2 diagonals. Whereas with something more simple like water, there only exists 1, and that's straight down the center. So we call that its molecular axis. Also, in order to be a liquid crystal, it cannot have a 3D crystal lattice. So now the requirements are over, let's look at how they actually work. So in a phase diagram, liquid crystals would occupy that red line there, which is between solid and liquid, obviously. So we use the term mesophase because it sits between the 2 phases. These aren't requirements, but some common characteristics of liquid crystals include a rigid long axis, strong dipoles, and a rod-like structure, and we'll see why these are important later. Now, on screen are 2 examples of liquid crystals, which are very different. One we would call calamitic, meaning rod-like, and one we would call discotic, meaning disc-like. In a classic solid, particles are fixed and well ordered, and the opposite is true for liquids, which are disordered and move a lot. Now between these two is a liquid crystal, which are ordered but still move quite a bit, hence liquid crystal. And because it sits somewhere between these two, we call it a mesogenic state. Again, we went over mesogen earlier, which means like halfway. I tried to draw this next bit as well as I could, but I just couldn't pull it off, so instead I've pulled a photo from the internet. So here we have the 3 different types of liquid crystal arrangement: pneumatic, smectic, and cholesteric, which is working from left to right. It also increases in opacity, which is to say it decreases in transparency from left to right. Because of these arrangements, liquid crystals have quite weak intermolecular forces that can be disturbed by electric fields. Remember when I said they had really strong dipoles? Yeah, well, when you apply an electric field, like this one here, they will turn towards, obviously, their respective poles. And this makes them useful for technology like calculators, phones, TVs, and multiple other things, which you may have heard is called an LCD. And if you've ever damaged your phone screen, which I have multiple times, if I'm being so honest, you will know what it looks like. Cholesteric liquid crystals reflect different wavelengths of light depending on their pitch, which makes them useful for thermometers, mood rings, and some liquid crystal displays. Whereas smectic liquid crystals will form layers, like soap, which is actually where it got its name from. If you've ever looked at the bottom of a soap dish and you see that little flaky stuff at the bottom, that's where the word smectic comes from. Liquid crystals, like any solid, will resist any changes to alignment you make with it. But unlike conventional solids, there are 3 possible changes, which we call curvature disalignment. There's splay, which is just bend, twist, which is exactly what it says on the tin, and bend, which is like stretching out the top. And because of these, elasticity is far more complex for liquid crystals than it is for conventional solids. It's because of this complex elasticity that allows it to be so useful. Conventional electromagnetic wave acts in all planes, but here I've just done vertical and horizontal. If you were to pass it through a polarizing filter, also called a Polaroid, you would cause it to only act in one direction. If you were to add a second Polaroid facing the opposite direction, you would eliminate the wave completely. Now, if you were to add a microsoap slide with water on it into the middle, nothing would change. However, if you did the same with liquid crystal, some light would come through. So this must mean that depending on the alignment and direction of the liquid crystal molecules, light will sometimes change polarities. And we call this phenomenon birefringence. It's because of birefringence we can look at a liquid crystal through a polarized microscope. And when we do, we end up with some beautiful looking thing like this. Now, the difference in colors is caused by variety in thickness in the liquid crystals. The little black line junctions are called topological defects, and what this means is that the crystals can't align in the structure. But it's not impossible for them to, and if you were to look at a liquid crystal sample under a microscope for a prolonged period of time, you would start to notice these topological defects disappearing. It's because of this that we can have multicolored LCDs. But if we go back to our example from earlier, if we shine light through a twisted LCD with two oppositely facing polarizing filters, light will get all the way through because the light will twist as it goes through the LCD, and so will come out the polarizing filter at the top. Now, if we close the switch, all the molecules align again, and all of a sudden the light doesn't twist, and so no light comes out the top. So that's it, right? No. Notice how I said the word topological? Comes from the word topology, which means shapes and stuff. And topology says you can't turn a sphere into a torus unless you put a hole in it first. So how does topology influence LCDs? Well, most LCDs nowadays are on flat surfaces. Think of phones, tablets, whatever. And that's because on a flat surface it's easy for all the liquid crystals to align, and so easy for them to generate images. But in, say, a sphere, there'll always be alignment defects around the top because they'll all be facing different directions. But we can generate spheres from flat surfaces using something called microfluidic techniques, which is something that deserves its whole own video, which maybe I'll do in June. Overall, there are two types of liquid crystals. There's lyotropic, which varies with concentration, and there's thermotropic, which varies with temperature. Today we've gone over thermotropic, but the thing with lyotropic is it assumes with any solution that any dissolved particles will at some point cause enough order in it. And so when you increase the concentration, you increase the number of particles that hypothetically have an order within the solution. And nature has loads of examples of liquid crystals. For example, rather than a pigment in its skin, the colour from beetles comes from a lyotropic liquid crystal that exists in its shell, which I just think is fascinating. I'm kidding, of course. What do you think I am? Some sort of biologist? Gross. So we're going to stop there. Thank you so much for watching. I hope you enjoyed. Please remember to like and subscribe. And starting next week and all the way until June, we're going to be doing A-level revision. So for those of you who have done their A-levels or are nowhere near their A-levels or don't take chemistry, feel free to skip the next couple months. But if you want to stick around, I'd appreciate it. So I will see you next week, possibly. Thanks for stopping by. Bye.